developer advocate with Temporal, and I'm here with Sergey. You want to take a moment and introduce yourself?
Hi, I'm Sergey Bykov. I've been with Temporal for 3 years now. I'm leading architecture for a cloud service.
Awesome. And speaking of a cloud service, and our cloud service specifically, there's a lot of thinking and a lot of things that go into building one. And so that's what I wanted to talk to you about today is what did we consider and what did go into building Temporal Cloud, since there's a lot there. And Temporal itself is this wonderful thing for providing durable execution and long-running processes and doing multi-step things. And that starts to sound a lot like managing infrastructure. And so can you talk a little bit about how we thought about creating a cloud service from the ground up, and then we'll get into some of the details?
Yeah, so that's the talk I gave last week at KeyCon San Francisco. We can use some of the slides I presented there as background. But if we step back, kind of going from the first principles, a company likes to talk, what is the problem, business problem we're trying to solve? Right? At the core of it, we have a product, like in our case, Temporal. It can be like a database, it can be some queuing system. So have beautiful, great open source or closed source product. Now we want to monetize it. And the popular way is to offer a hosted service.
Right.
So people can go and use it and without building their own infrastructure. So the question becomes, how do you build this kind of service?
Yeah. Yeah, and so then I'm thinking if I have a relatively simple service like a data store, like I could just say, here, this is your table, or here, this is your database instance. When we talk about something like Temporal, and if you've ever self-hosted things, you kind of know where I'm going with this, but when we talk about Temporal, there's a lot of extra services, not extra, there's a lot of services together that make up the server side. And so what do we start to think about when we're looking at the thing that we're deploying, the infrastructure that we're deploying, and how does that map to customers that are using it?
Yeah, and there's like two very related questions. Like the first one is about tenancy model, because the easiest and the most popular option, kind of in early years or decade of cloud, was to just offer kind of infrastructure as a service. You get a single tenant instances of hardware, like you get physical database deployed on a number of nodes. Right?
So this would almost be like a colo sort of thing. Like, this is your server.
Yep. Yeah, exactly. This is your essentially cluster. Right? And it's a very compelling model because it maps one-to-one to, like, if I were to self-host it, that's the same thing.
Yeah. And
it's isolated. So like I don't have to worry, only I have access to it. Other tenants have their own instances. But the model has downsides. The biggest downside is very expensive.
Absolutely, and so you can see in the slide here, like you provision way more than you actually need at any time.
You can provision way more or a little bit more. It doesn't matter. You have to pay for this essentially fixed cost, no matter what your usage is. The usage usually fluctuates, like over the course of the day, week, some spikes on some Black Friday kind of events. But the second part is headroom. Like you provision, yeah, you over provision a little bit, but then you cannot spike. Like if Black Friday, oh, now you need to provision infrastructure to have this headroom. Or if you always run at the Black Friday level, like how do you like scale it down?
Right. Right. And so then if we're talking about the downsides of the single tenant model, obviously the other side is the multi-tenant model. And the first thing that I think about when I hear that is the noisy neighbor problem of someone else unrelated to me is going to cause my performance to degrade. And so that's one of the major challenges in a multi-tenant service. What was our process for thinking about, and what did we go with in terms of trying to tackle that?
So there's sort of customer-facing like concerns, and then there's like the hosted concerns here. We went sort of the obvious way. We talked to customers and asked. And at the end of the day, we discovered even people that initially talk, oh, I want my own instance. Once they realized that we have to pay for it, and then once they understood sort of the trade-off, pretty much everyone turned back and said, no, I want to have my multi-tenant system. So that essentially pay as I go. It's a consumption-based model. And it aligns with business, and it's easy for them to convince their management because they say if our business grows 5x and our cost of this hosted service grows 5x, it makes perfect sense. If we have to spend this cost regardless of our business up and down, that's very concerning.
Yeah, absolutely. And so moving us forward a little bit, then with traditional infrastructure again, and I'm thinking databases and VMs and servers, there's a clear unit of customer usage. We have the database, we have the server, we have the scaling group, we have the load balancer, whatever it happens to be. We have these individual units. What was ours, and how did we go into provisioning that?
Okay, so one thing to touch on this, which kind of connects to your question, which is the headroom. If we offer, instead of offering physical clusters or servers, databases, we offer virtual database or a table or kind of maybe like a queue topic, then we can pack those customers to the same infrastructure. And because we have many customers, statistically, they're unlikely to raise their consumption. And so we can have this headroom where they can spike much higher than in a single tenant product, because the cost of that headroom is spread across everybody. So it's much cheaper, so it gives them better experience.
Right.
Right, and that's where we go to, like, what is the unit? Like, what do we provide? In our case, the answer was very simple because Temporal already had the notion of a namespace as sort of, even within self-hosted, the unit of isolation where like naming of your workflow IDs is unique within the namespace, and already control knobs for controlling throughput and other parameters on per namespace. It was a natural choice for us.
Yeah, and I again think of, like, if I were to self-host this, there's a lot of work that goes into provisioning an extra namespace. And so when we're thinking about providing the platform as a service to our customers, it sounds like then namespace as a service, like we will provision the namespace on your behalf as part of the service.
Exactly, and this is where, like, it's important to get into this distinction, which most people are familiar with, but that was my assumption, but when I presented this and talked with people, not everyone was actually familiar with where it came from, the notion of data plane versus control plane.
Right.
And I use the analogy of the telecom industry, where I think we borrowed this terminology as the industry at some point. Like, you have physical infrastructure, like switches, like your phone connects to a particular base station, it connects to switches and routers, and that's where the traffic goes, like whether it's phone call or text messages or internet. But then there is invisible control plane that manages like handoff of your call from base station to base station. Or, like, example I use, like, if you transfer your phone number from AT&T to T-Mobile or the other way around, it's actually two control planes that do a lot of operations reconfiguration to ensure that you have uninterrupted service even though you switch provider completely.
Yeah.
So it's like this physical world where signals or data flows, data plane, and there is the brain of the system that manages, controls, monitors, reconfigures, deploys new instances, retires, all of that is control plane.
Yeah, and so in Temporal Cloud, or Temporal generally, what is our notion of the data plane versus control plane?
I showed this sort of simplified diagram of what unit of temporal, the physical unit of Temporal Cloud. We call them cells based on this cellular architecture notion, where we want units to be as independent from each other in terms of failure or misconfiguration. And in temporal world, the cell looks like this. In the AWS, each cell has its own AWS account, so it's isolated as much as possible. A VPC, virtual network for isolation, EKS clusters for isolation. And then there's a bunch of stuff like compute pods that run both for temporal, for infrastructure. There's a couple of databases we use, and we have our own like journal layer in between. So all of this complexity just to comprise a single physical instance.
Yeah, but when we isolate them through all of these layers, then when one cell goes down, it's not going to affect someone else or another cell.
I think it's hard for it to go down, but if it's affected by, if there's like any configuration, there's any degradation of traffic, like in this virtual network, it's less likely to affect others. Or if this Kubernetes cluster is getting upgraded, that that cannot affect other Kubernetes clusters. So yeah, but the idea is the same.
Right. Okay. Awesome. Yeah. So let's talk a little bit about what it means to start deploying this, because it is a lot, and there is a lot going on here. So what goes into that? What goes into actually managing this and getting it out there?
Yeah, exactly. So the user experience is, we run ourselves like 10 or 11 regions in AWS. Right now we're working on GCP, but the user goes to Temporal Cloud UI, says, I want to create a namespace, and they pick the region, they give a name, they provide maybe like certificate information, and then they click a button, create namespace.
And then magic happens.
Right, and then I showed like a list of steps that we have to go through. Because we have multiple cells in the region, we need to pick one. It's an easy local decision based on like load characteristics and size and all that. But then we need to create a bunch of artifacts. Like we want to register a DNS name, we need to provision certificates like for MTLS. And then you go to the bunch of this API calls to, some of them go to AWS services, some go to other external services like Let's Encrypt. And they all take time, they may occasionally fail, they may occasionally throttle you. Like you get into this like laundry list of things that need to succeed eventually.
Yeah.
Not instantaneously, and they're all like distributed systems kind of challenges where—
Especially I'm thinking like DNS, which can take a very long time and to propagate it, etc.
And so to ensure that it all completes correctly, at the very end, we perform checks of connectivity. So we have two endpoints, one for gRPC, one for HTTP, and we go and check, oh, can I connect to it? Can I connect to it? And until we can connect to both of them, we don't say namespace is ready.
Right.
So that's why it's a kind of like the kind of long, not long in terms of execution, but in terms of writing code, there's like many, many steps, and all of them need to succeed.
Yeah, and so when I think about creating this and doing this control plane work on my own, I've said this a couple times, but there's a lot there, and home rolling the code and the systems to manage this and make this, as you said, there's a lot of retries, there's a lot of waiting, there's then the risk that the infrastructure that's running the control plane provisioning infrastructure is going to itself have problems. And that makes me sad and worried about what things are going to go wrong. I would much rather, this is starting to get into our standard temporal story a little bit, but like I would much rather think about just the happy path going step by step through. And what did that look like? Are we using temporal to manage temporal, and what does that look like?
Yeah, you're absolutely right. So kind of the solution that people want is kind of happy path where like steps are retried and then continue after the previous step succeeds, and it kind of leads to this sort of workflow-ish style. And you mentioned that it's tempting to hand roll something simple, and in my experience, it's pretty much always a mistake.
Right.
Because it's easy, quick to build something basic, like, oh, I'll checkpoint here, I'll check there. If I fail, like if I restart, I load, I know where I'm going. Oh, yeah. I'll record this timer.
And then I'll recheck that things are up and not, and yeah.
So the initial version will work with some effort. The problems are usually like, they surface like, 2 years later, where suddenly you need to add a lot more features and the code is brittle because there's all this kind of hacky assumptions, and the person who wrote the code already left the company, like things like that. And this is where like this hand roll solution, like I've seen many literal examples of that. It becomes unmanageable and people like stay away, say, we don't want to touch this code base.
Yeah. And
the only solution is to replace it with something. So for us, the choice was easy, and it was not an ideological choice. It was literally the benefits of durable execution shine in these scenarios.
Yeah, and so that helps us then get away from this unvirtuous cycle of home rolling something, it gets antiquated and brittle, so we deprecate it, and we home roll a new thing, and then we deprecate it, and then we home run a new thing, just like years and years of this replacing. And so we're trying with durable execution to get out of that cycle.
Exactly, and people start building something with even worse than rolling something hand roll. Like, oh, I'll just duct tape with some queues. I'll just queue, and then the queue will retry.
Yeah.
And I had many conversations like at Econ, people like, oh, they admit we've done that. Oh, we're in this phase of having queues.
Yep. We added Kafka and everything, and it's much better. Sort of. Okay.
Yeah. How do you see where you're at? Like,
yes.
You cannot, right? And with durable execution, like you can literally look at the screen and see, okay, it's at step 13. The last there code was, I don't know, dependent service unavailable. Next retry is like 5 seconds later. Like you don't have to write code for that. It's just so obvious.
Yeah, and I know you had mentioned earlier checking that the gRPC endpoint up or is the web endpoint up. And I know you had showed me earlier before we started recording about the code that's actually doing that for us. If we take a look at that, we were able to just look at, we have the straight linear progression of events that have happened, and there's no retry code that we wrote as the users of this workflow, right?
Yeah, that's why it's included in my slides, like screenshot of like the whole code of this function, like at top level. Not that it's readable at that font size, but to say like it's kind of flat and linear, more or less. And then when you show side by side the web view of that execution, that's literally events numbered. Like I mean, if you use Temporal or a similar system, you're familiar with notion of event history. That's literally what happened, in what order, and what time, and what payloads, arguments, and outputs were.
Yeah, and this is so much nicer than like if we did have a queue where we might have visibility into the list of messages that were in the queue or are in the queue, but it's mixed up between all sorts of different things. Whereas when we look at the event history for a workflow, it's one instance of that workflow. It's one execution of going through that control plane provisioning.
Oh yeah, I gave a whole separate talk on that, just to show like, look, like it's easier at one queue, but then you have a sequence of queues. Like you can see that queue length, right? You can see how many messages, but you cannot see what exact message is or how many times that message got re-enqueued. Yeah. All of that is unmanageable. Yeah, in this workflow history, it's very easy. And I zoomed in on this one point or one step on a provisioning namespace where we actually check connectivity. It's literally this few lines of code where it says retry indefinitely and check gRPC. Indefinitely means until we reach timeout of the whole provision, whatever we set. Say we will wait up to half an hour. If not, then we'll page engineer, and then we'll try one endpoint, try the other endpoint, and until they both succeed, we'll hold
just keep trying.
But the code, like you said, the code we write is happy path. Like it needs to succeed.
Yeah, exactly. I don't see any like exponential backoffs or anything along that line of it's just try it. And that's it. It's great. It's lovely.
Same in the web view, where like, okay, this action can finish 20 seconds, like the second check completed successfully 20 seconds after the first one because they got available at endpoint at different times.
Perfect. And so for our audience that is familiar with Temporal, we have a lot of distinctions here between workflow and activity. And one of the questions I see a lot is, what should be in the workflow? What should be in the activity? What should go in a child workflow? How do I segment these things? How did we segment these things? And where did what go in this case? So like I see that the web and gRPC endpoint checking is an activity. Where did everything else land up?
Yeah, that's one of the key choices when designing temporal based code. Activity, like we have rules for it. It needs to be kind of stateless action that idempotent, so it can be retried many times, and that allows the runtime to execute it many times without us writing code for that. And workflow, it's more stateful code where you can have variables that get reconstructed if you recover, and that organizes the logic of what actions, what activities need to be called, and how output needs to be processed and sent to another step. When it comes to what needs to be child workload, that's totally, it's like functions of functions, usually that some boundaries that are logical for a particular use case, particular task, right? Like for example, if I'm provisioning endpoint, it makes sense to put steps related to endpoint in one workflow so that can be tested independently from provision other artifacts, for example.
And so this is more or less just our standard software engineering separation of concerns. We want to make sure that one unit of whatever it is concerned with one thing.
Or what we teach people, or try to teach early on, that the most important quality of code is maintainability.
Right, yes, absolutely.
If somebody else can come and see and make sense and make changes to it efficiently, that's good code. If it's clever algorithm, nobody else can figure it out.
Right, yeah, exactly. And it could be just the most clever one line and it's never going to be maintained.
Yeah, that's why it's for structuring your code, just like you said.
Yeah. So this is great. And if I take out some of the our use case specific jargon here, like namespace, this looks pretty standard. Like there's not much unique here per se to us in our hosted service. And this is obviously a little bit of a leading question, but like where else do these patterns show up, and are there other people doing similar things?
That was kind of the motivation for my talk, not to go and just say, hey, here's what we build. So that would be kind of curious and interesting, but the motivation was that it's a pattern, that we're not the first to discover it. I was clear to talk about 5 companies, by our marketing go-to-market team, that built their control planes for their product. Like Red Panda is kind of like a Kafka queuing system, and they offer it as a service. I mean, everyone knows Netflix, everyone knows Datadog, Cache, Chronosphere, that's the ex-Uber database for metrics. In all the scenarios, they need to manage a bunch of kind of physical resources. Even though in cloud they're kind of virtual machines, they're physical resources. You need to provision them, you need to set up your software, you need to manage your software, all exact same problems. And some of them started before our cloud and built this control plane. So it's not like we were smartest kids in town, and no, we didn't invent anything here. We're just sharing the pattern that other people applied.
Yep, absolutely, and that's where some great innovation come in. It's just like iterating on a pattern and making that easier to roll out.
Yeah, our goal is to make developers more productive, and when they need to write less of glue code, less of this kind of boilerplate code, that they're happier and more productive.
Yeah, absolutely. And speaking of developer productivity, one of the questions that I often get when talking to developers and introducing Temporal, especially when things can potentially take a long time, like waiting for DNS, it's always, but things change. My version needs to be updated. My Kubernetes cluster needs to be upgraded. Something needs to roll out after I do the initial rollout. And there's a lot of extra concerns, not just doing it once, or repeatedly once, but also then upgrades and maintenance and things like that. So when we are rolling out a new version of this, a new version of the infrastructure and of the namespace, what does that look like?
Yeah, that was the second scenario I covered in my talk. How do we roll out, in this case, like new version of Temporal server, right? So we have a bunch of pods, bunch of cells. We organized our cells into deployment rings. They numbered from 0 to whatever, infinity, I think highest 999. But it's like maybe half a dozen or a dozen rings today. The approach is, again, very simple, that you put your least critical resource in lower rings and most critical in the higher rings. And you do essentially roll in upgrade by rolling out your changes to lower rings first, and our ring 0 is pre-production. These are cells that have no customer traffic, but they have constant synthetic traffic. So like when we roll out a new version, the standard procedure is that we rolled out to ring 0, it stays there for a week. We say we bake it there for a week, and if anything, we'll discover. And then we start slowly rolling to other rings.
Yeah, and so this is then where a lot of our standard deployment patterns come in of Canary and Blue-Green maybe come in?
I'm not sure Blue-Green fits here.
Okay.
No, it's kind of in place upgrade in this case. It's more like rolling upgrade.
Got it.
But what's distinct here is that we have to wait.
Yeah. And
we wait because some bugs that may manifest like over several days. If you have a resource leak or you have something probabilistic takes time to happen, like the only solution there is be slow and conservative.
Yeah, that makes sense. So then what is that, what are those step-by-step processes for getting through rolling out to a particular ring or a particular server version?
Yeah, I showed this sort of embarrassingly trivial algorithm with 4 nested loops. So for each ring, we go and sleep between rings. Then we take a batch of cells within that ring, because we don't want to blast and touch all cells at once. That would be violating the cell architecture principles of isolating. Then we go through the cells, and within each cell we go through services. Like in this case, temporal, we have front end, history, matching, worker. So those we want to also like upgrade one at a time.
Right.
And so there's a lot of like sleep time. And so this whole rollout of a version to the fleet may take easily 2 weeks. Which imagine like if we were to write a normal process program that has to stay up and run these loops for 2 weeks.
Yeah, it's never going to happen. Yeah.
You get upgraded 10 times.
Absolutely.
And like for durable execution, it's trivial, right? You just write this and say, I'm going to sleep for like a few hours, and then I'll continue to the next step.
Yeah, and can you address briefly, if I'm upgrading temporal with temporal, like what is there a separate infrastructure temporal server that we're using, and like where are we running our temp version and our workflows?
Yeah, so I showed this kind of picture. I mean, of course, it's simplified for the screen presentation. So we have control plane namespace where we run these workflows, for example, like rollout, that goes through this whole loop of, actually we collapse that loop. I can show a screenshot of the code. But it goes and then calls into this per cell entity workflows.
Okay.
They're kind of singletons. I can talk more about it. And then within that cell workflow, which is like managing an individual cell and guarantees the concurrency control, at some point the call happens to another namespace, to another API. We call it infra API, the infrastructure layer, which runs in a separate namespace and has a bunch of workflows to actually go and send Kubernetes commands.
Okay, yeah, and so that's that entity idea is, and you use this term, and I've heard it before elsewhere, this device twin idea of maybe if it was borrowed from IoT, maybe it would be a sensor out in the field, but in our case we're using it as this is a cluster.
It's near dear to me because I think the old name for entity workflows is actor workflow.
Yes.
And I spent a number of years working on actors. So the point is that if we allowed concurrent updates to the same entity, like same cluster, same namespace, we'll be asking for disaster. Like, or we'll have to have like a distributed lock or some sort of protection mechanism that difficult to get right and like complex. Here, temporal guarantees it has a very strong guarantee of a single instance of each workflow with the same ID. And so, like, if we use that workflow with that ID, we guarantee there is no 2 instances running. And like, whenever I send a signal to it, it will get to that instance, and it cannot interfere with anything else. So the guarantees of a program model have a lot of power here.
Yeah, and that helps us reason about things in a much easier fashion when we're thinking about one workflow is doing one thing in this order rather than multiple things at once.
Right, the code becomes very explicit and very much easier to get right than if I have to think about threads and like, oh, what if, and then the code evolves even if I had it correctly with some locks and somebody changes them.
Right, and now I'm deadlocking and my queue is overflowed and all these other problems. And speaking of the code, like we do have some screenshots of the production code to look at here. And I love looking at this code because this was similar to the gRPC and web endpoint uptime checks, because it's just, here's our list of things, loop through them, and that's more or less it. It's such clean code.
Yeah, I mentioned that here we have a single loop because this is where like implementation by engineers is actually more optimized than this conceptual 4 nested loops. But the engineer just collapsed them into like the batches and get the list of all batches of all rings and everything with timing attached. So like we have a single loop, and this is like exact snapshot from the production code that will loop all these batches. And this loop, like I said, will run for like 2 weeks, and it'll be fine. Even if we shut down and restart and upgrade control plane, it will just continue.
Yeah, it's fantastic. So what have we learned through all this? Like what is the big from making the decision to deploy multi-tenancy to rolling these things out, using Temporal itself? What are some of the major learnings that we've got from this?
The first immediate learning I mentioned was that people want multi-tenanted services, even though it may be counterintuitive sometimes. They want to pay as they go. The consumption-based model is pretty much everyone. Even the big banks that seem to have unlimited budgets, they want consumption-based. And then I wouldn't say like we learned, we kind of knew that. It just reinforced that writing the code for these kind of problems, solving these problems with durable execution, it's, I don't want to say pure joy, but it's kind of close to that, because by removing a lot of boilerplate and making this code manageable, like the example that blows people away, like if we have a bug in our code, like we call an API, it's not even a bug, but the API we call it change, and now the code, that activity that makes this API call will never succeed. We can see it in the web page. You say, okay, it's failing with its incorrect arguments. We can go change the code, deploy new version of that code. They will continue because the line will succeed after like maybe 50 retries. So that magic of fixing code in place, that makes developer like productive and happy.
Absolutely, that's that happy path again. That's so great.
Long running operations. Again, we knew, but we experienced it ourselves. It's something that takes hours and days. Being able to just run it and then see, like, I showed the example, like the screenshots where this rollout workflow, it posts in Slack channel, say, hey, I'm here somewhere.
Right? Got it. Yep, we're right there. Yeah.
So, yeah, I'll upgrade this cell at this time, like 17 hours later. For us, it's normal, like 17 hours. There's no concern that something may prevent it from happening.
Yeah, absolutely. And if I were to write this without Temporal, I would like sleeping or waiting for 17 hours. Like I'm scared that that's not going to work.
Of course. And then the sort of another takeaway that you mentioned is that people discovered that independently from us. So the durable execution, whatever tools you use. I mean, I was told that in AWS, a lot of internal control planes are powered by a simple workflow. For all the same reasons, because of this durable execution model is good for building control planes. And I show like 5 examples where companies, they have very smart engineers. They made the same choice to build their control planes and make their life easier and happier. Yeah,
absolutely. I want to take a brief detour a little bit, and we mentioned entity/actor, and that in my head is a great example of a long-running workflow, because it's something that we really want to have existing for an unknown amount of time. Can we take just a brief dive into that, and like what does that look like in Temporal? And like the term workflow speaks to me as a series of steps of things, and that's kind of an entity, but like when you think about representing a workflow as an entity, let's talk about that.
Yeah, like I said, this topic is near and dear to my heart. Entity workflows is just a pattern. It's not like there is a primitive or anything. It's just a pattern of leveraging this uniqueness of identity of the workflow, and the fact that it can run forever or can start again with the same identity, guarantee there is no concurrency. And there are options there. Like, for example, in the forever running workflow, I was told that at Uber, for example, loyalty points, they, like when you take a trip and they add points for that, all the state for each user is held in the entity, like user workflow for that user. It's like whatever hundreds of millions of users, the state is nowhere in the database even, which blew my mind. It's only in the workflow state that keeps running forever.
Yeah, and so since we've got all that information in the event history, then we can just recreate that any time that we need to.
Right, and they can continue as new to like essentially snapshot its history and continue. So that's one option where people go all the way to keeping older state in the workflow.
Yeah.
The other option is to externalize the state and put it in the database, like for a different reason, like maybe you can query it independently. And we tried both. We started with holding state within the entity or closed state, and then we ended up switching to the second pattern where state is actually in control plane database for like each cell, each user, namespace. And so when you invoke the entity workflow, it starts, first thing it does, it loads state from database. And because it's a single writer, there's no concurrency, like control issue. So when it applies a change, like for example, update like access to the namespace, saves it to the database from that single instance. Now database is updated. If it restarts next time, it will get the state from there.
And that's such a clean model, again, to implement this.
It's clean, but one feature was missing when we started. So there's this notion of signals, of course, in temporal, and when you send a signal, like how do you get a response? We request to roll out this build, right, or update this cell with this version. Okay, that update may take an hour. How do we know that it's done? Because polling is inefficient. If we need to, we can use a signal back, and then we need to set it up all this kind of machinery. Back then, there was no workflow update feature. And so we ended up building an internal library for sending a signal request and waiting for a signal with the response and wrapping it up. So essentially, it's kind of RPC-like experience. Which now you get with update.
Right.
And to me, that completed the picture of entity workflow as an actor. And if you externalize state as a virtual actor, where you can always call it, and you call to his RPC library, which sends signal with start. If workflow is running, you'll get a signal. If it's not running right now,
start it up.
You will start, will load state from the database as if it was running. So like the caller doesn't need to know, it doesn't need to create it. The caller just called, do this for me, doesn't need to worry whether this workflow ever ran before if it's running right now.
Yeah, and then as we mentioned, we guarantee there's exactly one of that instance of the workflow, and so then we only have one writer for that mapping of the cluster or whatever the device is.
Yeah, you can imagine the whole host of concurrency issues that just have no chance of appearing. And scalability-wise, it's great because you have, I don't know, thousands, depending on what kind of entity type, hundreds, millions of these entity workloads. They can be run on cluster independently.
The horizontal scaling there that we can do is amazing.
They embarrassingly parallel because they don't share anything.
Right, absolutely.
So that's like this pattern, I think, is very powerful. Digital twins, you mentioned IoT, but it's actually like anything, like the user, right? It's not IoT, but having a single, essentially a resource guardian for a user or for any other resource, like a Kubernetes cluster, that's a powerful pattern. That's why I wanted to talk about it, even though like the whole talk was about control plane, but it's an important pattern. Yeah,
I think it is a very important pattern, and this whole talk has also been about patterns too, so it's a very important thing. And I've seen people talk about a workflow representing infrastructure in various ways, so I think it's very important to cover. Is there anything else you wanted to talk about or mention?
Well, I want to kind of emphasize what you're saying. Like, there's a bunch of patterns. Like, it's not like we invented a pattern here. But if you think back, even like temporal and durable execution, there's no like a computer science invention there. Like, it uses event sourcing underneath. It has all this kind of concurrency guarantees and all of that. But what you get there is that it lifts a level of abstraction for what developers use. It's just normal progression, like from assembly language, like to like C to like other high level languages. The same thing, to encapsulate patterns, and instead of people thinking about sending messages, having like event-driven architecture or event message passing, you deal with your business logic. You need to execute these 5 actions, and you don't want to deal with boilerplate code.
Yep, absolutely. All right, I think that covers everything. Thank you so much for taking your time with me, Sergey, and I appreciate everything that you worked through with this.
Oh, sorry, absolutely my pleasure, and like, as you can tell, I'm really passionate about this topic. I'm always happy to talk.
It's a fun topic, so thank you.
Right.
All right.